Welcome to today's session on National Industrial Conference. My name is Santosh Raikar, and we're going to dive into the true engine of asset reliability, the journey from a condition monitoring alarm to completed work. We often focus on the gadgets and the graphs, but today we'll discuss why detection only earns you time, while it is the completed, verified work that actually creates reliability. We will trace the entire path from the P-F interval through technology selection, diagnosis, and finally, repair verification. Let's start with an uncomfortable truth in our industry. An alarm that simply dies in someone's inbox creates zero reliability for the plant. While modern sensors are incredible at detecting physical changes, they are just the ears of the operation. Without a disciplined work system to convert those signals into avoided failures and safe execution, the data is essentially wasted. Reliability is a human and systemic discipline, not just a digital one. To fix this, we need to view condition monitoring as a closed-loop decision and work system. It isn't just about detecting a problem. The loop begins when a change appears, but it must pass through validation, diagnosis, and risk ranking before a single wrench is turned. Most importantly, the loop only closes when we measure the repaired asset again. If we don't verify the as-left condition, we haven't truly protected the asset's function. Our roadmap for today follows 5 acts. First, we'll understand the P-F interval, which is your window for making decisions. Second, we'll look at selecting the right evidence through the correct technology. Third, we'll cover the discipline of diagnosis. Fourth, we'll discuss how to turn that technical diagnosis into a decision-ready work order. And finally, we will look at verification, confirming that the problem is actually solved. Let's start with Act 1. The P-F interval. It's vital to remember that the time between potential failure and functional failure isn't just a countdown to a crash. It is your logistics and decision-making window. If your window is 10 days, but your parts take 20, your monitoring strategy is already broken. To use this window, we must distinguish between potential failure and functional failure. Because when we find evidence that degradation has begun, though the machine might still be doing its job. F is the point where it can no longer meet the performance standard. Perhaps it's pumping less flow or creating quality issues. Our goal is to make P as specific as possible, so we have a clear reason to act before F occurs. Think of the P-F curve not as a promise of exactly how many days are left, but as a conceptual tool to visualize your reaction time. From the moment we detect a change of point P, the clock starts ticking. That interval is the only time you have to validate the data, plan the job, and execute the repair before the asset loses its function. The best way to manage this interval is to break it down. We shouldn't spend the time on administrative delays. T1 is for validating the sensor. T2 is for naming the failure mode. T3 is for the logistics, permits, parts, and access. And T4 is the execution. If we streamline the first 3, we maximize our chances of completing the repair while the asset is still healthy enough to be fixed safely. A practical rule of thumb is that your inspection interval must be significantly shorter than the expected P-F window. You need multiple chances to catch the problem. This interval isn't fixed. It changes based on the load, the environment, and how sensitive your technology is. If you find you can't respond in time, the monitoring task itself is poorly designed and needs to be adjusted. Monitoring is essentially a game of probability. It is far safer to have several okay chances to detect a fault than to rely on one perfectly timed visit. By setting a frequent enough cadence, we create independent detection opportunities that can absorb real-world issues like route variations, noise, or human error. We want to catch the trend across several checks, not just a single spike. Now, let's talk about strategy discipline. A common mistake is starting with a sensor catalog. You should always start with the failure mode. A technology only adds value if it produces repeatable evidence early enough to actually change a maintenance decision. If the sensor can't change what you do, you don't need the sensor. We filter our monitoring policy through 5 gates: function, failure mode, evidence, P-F interval, and finally the task. If you reach a point where there is no actionable decision possible, stop. Don't create a data collection ritual just for the sake of having numbers in a database. Data without a potential action is just overhead. To make sense of any data, you need a baseline. A baseline isn't just the first number you recorded. It's a record of a known good state. It must include the asset configuration, operating speed, load, and the specific measurement method. This baseline allows you to separate normal process variation from actual equipment degradation. Behind every data point, there should be a minimum amount of context. We need to know which component we're looking at, the operating state, like 73% load, and the sensor settings. This context is what makes data reproducible. Without it, you can't tell if a vibration increase is a failing bearing or just the pump running at higher speed. This brings us to Act 2, selecting technology by failure mode. Different problems leave different fingerprints. A world-class program doesn't force one tool, like vibration, onto every asset. Instead, it combines technologies selectively based on how the machine is likely to fail. When selecting technology, follow the evidence chain. Start with the mechanism. Is it wear, friction, or a leak? Then, identify the measurable symptom, like heat or sound. Define a threshold that triggers action. And finally, ensure your plant actually has the capacity to respond to that specific signal within the P/F window. This selector chart helps us choose the right first choice method. For example, while vibration is the primary tool for misalignment, ultrasound is often the earlier indicator for bearing issues or compressed air leaks. Infrared is king for electrical connections. Using the right tool for the right mode ensures you get the maximum warning time. Let's look at more complex scenarios. Cavitation might require a mix of vibration and process data. Gear wear often shows up in oil analysis before it's obvious in vibration. The key is to match the method to the specific mechanism so that the resulting decision is clear, whether that's cleaning a heat exchanger or planning a gearbox inspection. Vibration analysis is our most common tool, excellent for structural issues and rotating parts. However, we must be careful. Overall velocity alone is rarely a diagnosis. We need the spectrum and waveform to name a failure mode. It's highly sensitive to how the sensor is mounted, so consistency is everything here. Ultrasound is a fantastic early warning tool because it hears high-frequency energy caused by friction or leaks before heat or vibration increases. It's great for slow-speed bearings. Just remember that it requires consistent technique and gain settings, as airborne noise can sometimes mislead the analyst. Infrared thermography gives us a fast, non-contact visual of abnormal heat. It's the standard for electrical surveys. The watch out here is that temperature alone rarely tells the whole story. You have to account for emissivity and load. A hot connection on a motor running at 10% load is much more serious than one at 100% load. Oil and wear particle analysis is unique because it tells us about both the machine and the lubricant itself. It can identify the exact material that is wearing away. The biggest risk here is poor sampling. If your sample is contaminated during collection, you'll end up making very expensive, very wrong decisions. Electrical condition monitoring is growing in importance. It allows us to detect rotor and stator problems and even issues in the driven asset by looking at the power quality and current signatures. Because process loads can imitate electrical faults, we always correlate this data with mechanical evidence before approving a work scope. We shouldn't forget that process performance data, like flow, pressure, and efficiency, is also condition monitoring. Sometimes the best sensor is the one already in the SCADA system. If a pump's head is dropping, that might be a better indicator of internal wear than any vibration probe will ever provide. Operators are also high bandwidth sensors. They are around the equipment every day and notice changes in smell, sound, or behavior. To make this evidence scientific, we need to give them a structured way to report abnormalities with clear severity anchors like monitor or urgent, rather than just vague notes in a logbook. Your monitoring architecture should be a mix. Online systems are for critical, fast-failing assets. Route-based programs cover the bulk of the plant. Operator inspections provide the daily context. No single mode solves everything. The trick is to ensure that an abnormality from an operator triggers the same discipline validation as an alarm from a sensor. Data quality is the foundation. If you have bad sensor placement, you're just generating confident nonsense. We must measure as close to the load path as possible and permanently label sensor locations. If the operating state, speed, and load isn't captured with the reading, the trend is essentially useless for comparison. Finally, we use evidence fusion. We don't need every technology to show a fault, but we do want them to tell a coherent physical story. When vibration shows a specific frequency and the oil analysis shows the corresponding rare metal, your confidence in the diagnosis skyrockets, making the work scope decision ready. Act 3 moves us from alarm to diagnosis. At this stage, treat every alarm as a hypothesis that needs testing. Before spending maintenance resources, we must validate the signal and normalize the context. We need to be sure the problem is in the machine, not in the sensor or the way the machine was being operated. Alarm discipline is critical. An alarm is just a starting point, not a final diagnosis. Our first question should never be, what do we fix? But rather, is this signal real, relevant, and consistent with the laws of physics? We must prove this signal before we act on it. Good alarm design avoids chatter. We use delays and state-based suppression, so we don't get alarms during a normal startup or shutdown. The alarm message itself should be informative, telling the owner what the value is, what the baseline was, and what the likely failure mode might be, rather than just a generic high alert. We must manage the quality of our alarms. False positives, crying wolf, waste the team's trust and time. False negatives, missing a failure, are even more dangerous because they leave us exposed to risk. Both are usually caused by poor baselines or failing to account for the operating context. Validation should follow 5 discipline moves. Check the data integrity, check the machine state, repeat the measurement, corroborate with a second method, and then, and only then, make a decision. Every validation must end with a clear owner and a due date for the next step. Normalizing the operating context is vital. Vibration levels and temperatures will naturally change with RPM, load, and even the ambient environment. You cannot compare today's reading at 100% load to last month's reading at 50% load and call it a trend. You have to compare apples to apples. When diagnosing, we move from the symptom to the mode to the cause. If we just repair a symptom, like replacing a hot bearing without realizing it was misaligned, the problem will just come back. Reliability means removing or controlling the underlying cause, not just swapping parts. Diagnostic evidence escalates in levels. We start with the trend. Is it changing? And move to the pattern. What mechanism fits? And eventually to a physical check like a borescope or clearance measurement. This ladder of evidence builds the confidence needed to stop a production line for repairs. Signatures like harmonics or sidebands are great guides, but they don't replace engineering judgment. We use them to form hypotheses, not to blindly name a failure from single number. We should never hide uncertainty. If we aren't sure, we should state what extra evidence would make the decision clear. Prognosis, predicting remaining life, is notoriously difficult. It's always a range, not a specific date. A defensible forecast includes the current rate of change and an uncertainty band. Use this to decide if you need to secure parts now, or if you can safely wait for the next scheduled shutdown. Make your confidence visible. Low confidence means go get more data. Medium confidence might mean order parts but wait to schedule. High confidence means the fault is confirmed, let's execute. This transparency helps operations understand the risk they are carrying. In Act 4, we translate technical evidence into work. This is the bridge between the reliability lab and the maintenance shop. We need to turn technical findings into decision-ready work orders that fit into the existing maintenance operating system. Priority is more than just the loudness of a signal. It's a calculation of consequence, urgency, and confidence. A loud vibration on a non-critical backup pump might be lower priority than a tiny, subtle change on a critical main turbine. We focus on the risk, not just the noise. Using a risk matrix helps align everyone. Consequence is usually owned by operations, while urgency, the P/F window, is managed by maintenance. Remember, low confidence in a diagnosis doesn't mean the consequence is low. It just means you need to validate faster because the potential impact is still high. We must also distinguish between alarm priority and work priority. Alarm priority is about how fast we need to acknowledge the data. Work priority is about the logistics. What parts, what skills, and what production window do we need to finish the job before the F window closes? To simplify actions, we use 4 decision bands. Watch for stable issues. Plan for confirmed degradation with time spare. Urgent, when a window is closing fast. And stop, when a failure is imminent or safety is at risk. This language is much clearer for a scheduler than technical jargon. A decision-ready notification is far more than just saying high vibration. It provides the context, a specific diagnosis, like coupling misalignment, the estimated risk window, and a clear recommendation for the repair. This allows the planner to act immediately rather than having to ask for more information. The work order is the vehicle for the technical decision. It should carry the as-found evidence and the specific repair scope. Crucially, it must also define the as-left acceptance criteria so the technician knows exactly what a good repair looks like before they finish the job. Planning must happen within the F window. We calculate a scheduled completion date by taking the latest safe date and subtracting a reserve for uncertainty. If the time required for parts and permits is longer than the F interval, then monitoring alone cannot save you. You need a different strategy. In the digital age, we need a thread from the alarm to the CMS. By using the same asset ID and component model throughout the process, we ensure that every finding and every verification is traceable. This creates a history we can actually learn from. Backlog governance is where many programs fail. Condition-based findings need a protected path. We should age them by their safe date, how many days are left until failure, not just by how long they've been sitting in the system. And we must never close them administratively. They only close when the evidence says the risk is gone. Act 5, repair verification. This is the most overlooked step. A repair is an intervention, and we must prove that it actually restored the condition and removed the cause. Without verification, you're just hoping the repair worked. We have to instill a closure discipline. Work complete is not the same as problem solved. If you don't measure the asset after the repair, you've only closed the paperwork. The physical risk to the plant might still be there, hidden under a new coat of paint. We close the finding through 5 gates. Inspect the as-found condition to confirm the cause, execute the scope with precision, commission the asset, measure the as-left condition, and finally, update the baseline. If verification fails, we don't close the work order, we escalate it. The as-found and as-left evidence must tell a traceable story. We compare the parameters, the machine state, and the physical condition. This comparison is what allows us to confidently say the functional standard has been met and the residual risk is gone. Acceptance criteria should be defined before the repair even starts. We look for the condition parameter to return to the good band and for the specific fault pattern to disappear. We also ensure that no new defects were introduced during the maintenance process itself. For comparison to be valid, 3 things must be the same: the measurement technique, the operating state, and the question being asked. You can't verify a repair by taking a reading at idle if the original fault was detected at full load. Consistency is the only way to prove restoration. Every repair is a learning opportunity. We ask, did it recover? Was the diagnosis right? What was the actual cause? By feeding this back into the system, we can update our alarm thresholds and job plans, making the entire monitoring strategy smarter for the next time. A successful operating model requires clear roles. Analysts own the data quality, planners own the job package, and maintainers own precision execution. When everyone knows what they own and what the handoff standard is, the system moves much faster and with fewer errors. When measuring performance, focus on conversion and risk removal, not just activity. It doesn't matter how many points you collected if only 10% of findings are being converted to verified work. Mature programs track safe date compliance and diagnostic accuracy rather than vanity metrics like sensor counts. Let's look at a quick case study. Pump P204A. From the initial alarm on day 0 to a verified repair on day 12, the workflow remained disciplined. We validated, diagnosed a soft foot issue, ranked the risk, and verified the fix with as-left data. The finding was only closed once the vibration was back to baseline. You can build this closed loop in about 90 days. Start by stabilizing a pilot group of assets, then integrate the findings into your CMS. By the third month, you should be measuring cycle times and publishing success stories to prove the value before scaling up. Experienced practitioners know that technology isn't what usually fails, it's the process. Common failures include buying sensors before defining a response capacity or letting reports sit in a drawer. The correction is always the same. Pilot the entire loop from alarm to verified work on a few critical machines first. There are excellent international standards to guide you. ISO 17359 covers program setup, while the ISO 13374 and 13379 series help with data interpretation and diagnostics. Using these standards ensures your program is built on a defensible, world-class architecture. For those looking to dive deeper, there are fantastic resources available from industry leaders. I encourage you to use these videos as discussion starters for your teams. Always remember to adapt these general best practices to your specific site risks and asset designs. As we wrap up, here are 4 executive takeaways. First, detect only for decision. Second, spin the P/F interval on logistics, not delays. Third, ensure technical evidence becomes an executable work order. And fourth, always verify the as-left condition before you close the book on a repair. In conclusion, detection earns you the time, but only completed work creates reliability. Make your alarms actionable, protect your decision windows, and always verify your results. Thank you for your time and for your commitment to asset excellence. I'm now happy to take any questions.